What are the practical applications of semiconductor diodes? Diodes serve diverse functions across electronic circuits, including clipping circuits, rectifiers, voltage regulators, clamping circuits, or amplitude level shifters. Let us analyze parallel clipping circuits. A standard parallel clipper consists of a series resistor R and a shunt diode D, where the output voltage V sub O is measured directly across the diode. Consider a periodic input waveform V sub I, such as a sinus wave or triangular signal. Using the simplified ideal diode model, if V sub I remains below the cutoff voltage V sub gamma, the diode remains off. Under this reverse biased condition, zero current flows through the loop, causing zero voltage drop across resistor R. Consequently, V sub O directly tracks V sub I. Conversely, when V sub I exceeds V sub gamma, the diode turns on and is modeled by a constant voltage source V sub gamma. In this condition state, V sub O clamps precisely at V sub gamma. Therefore, as long as V sub I is below V sub gamma, Vout follows V sub I. Once V sub I suppresses V sub gamma, the output voltage is clipped at V sub gamma, resuming tracking when V sub I drops back below V sub gamma. Next, consider a biased parallel clipping circuit incorporating a DC reference battery. In this setup, resistor R is in series with a parallel branch containing diode D in series with a DC battery, V sub DC, where the positive terminal of the DC source connects to the cathode of the diode. Analyzing a periodic triangular input signal, the cathode potential is fixed at V sub DC. For the diode to conduct, the anode voltage V sub I must overcome both V sub DC and the cutting voltage V sub gamma. Thus, the conduction threshold condition is defined by whether V sub I is greater or less than V sub gamma plus V sub DC. If V sub I is less than V sub gamma plus V sub DC, the diode is off, no loop current flows, and V sub O equals V sub I. When V sub I exceeds V sub gamma plus V sub DC, the diode turns on, clamping the output V sub O strictly at V sub gamma plus V sub DC. As a result, the output waveform tracks the input whenever V sub I is below the threshold and clips at V sub gamma plus V sub DC during the interval where V sub I exceeds this combined value. In a parallel clipping circuit featuring a DC battery bias where the diode is reverse biased, the positive terminal of the diode connects to the positive terminal of the DC source. Assuming a triangular input waveform V sub I, the diode conducts only when V sub dc is greater than V sub I plus V sub gamma. Express it in terms of V sub I, the uncondition for the diode requires V sub I to be less than V sub dc minus V sub gamma. When this condition is met, the diode turns on and is replaced by its equivalent voltage source V sub gamma, fixing the output voltage V sub O precisely at V sub dc minus V sub gamma. Conversely, when V sub I is greater than V sub dc minus V sub gamma, the diode turns off, acting as an open circuit. Under this off state, zero loop current flows, causing V sub O to track V sub I directly. Consequently, the output waveform remains clamped at V sub dc minus V sub gamma whenever V sub I is below this threshold, and follows V sub I whenever the input exceeds V sub dc minus V sub gamma. Transitioning to series clipping circuits, the diode is connected in series with a resistor and V sub O is measured across the resistor. Here the positive terminal of the diode faces input sub Vi. For a triangular input V sub I, the diode turns on only when V sub I is greater than V sub gamma. When V sub I is less than V sub gamma, the diode remains off, resulting in an open circuit where zero loop current flows, dropping V sub O to 0 volts according to Ohm's law. When V sub I is greater than V sub gamma, the diode conducts and apply KVL yields V sub O equals V sub I minus V sub gamma. Thus, during the period where V sub I is less than V sub gamma, V sub O remains at 0, whereas during the interval where V sub I exceeds V sub gamma, V sub O follows V sub I minus V sub gamma. Furthermore, a series clipping circuit can be biased by adding a DC battery V sub DC in series with the resistor and diode. In this biased configuration, the negative terminal of the diode connects directly to the negative terminal of the DC battery. Consider a periodic input waveform V sub I, such as a triangular signal, applied to a series clipping circuit with DC bias. To determine the conduction condition for the diode, the voltage at the anode, which is connected to V sub I, must satisfy V sub I greater than V sub gamma minus V sub dc. When V sub I is less than V sub gamma minus V sub dc, the diode remains off and acts as an open circuit. Consequently, no current flows through the circuit, resulting in zero voltage drop across the load resistor, which sets V sub O equal to negative V sub dc. Conversely, when V sub I exceeds V sub gamma, V sub gamma minus V sub dc, the diode turns on. Under this condition, the diode is modeled by a constant voltage source V sub gamma, with its positive terminal facing the input. Applying KVL yields V sub O equals V sub I minus V sub gamma. Assuming V sub dc is greater than V sub gamma, the threshold value negative V sub dc plus V sub gamma represent a negative voltage level. In the region where V sub I is greater than V sub gamma minus V sub dc, the output waveform replicates V sub I shifted downward by V sub gamma. For the remaining portion of the period where V sub I drops below V sub gamma minus V sub dc, the diode turns off and the output clip at negative V sub dc. Now, consider rotating the diode by 180 degrees such that its cathode faces V sub I while its anode is connected toward negative V sub dc. For the diode to turn on, it is necessary that V sub I be lower than minus V sub gamma minus V sub dc. When the diode conducts, it is modeled by a DC source V sub gamma with its positive terminal on the right. Applying KVL to this state gives V sub O equals V sub I plus V sub gamma. If V sub I is greater than negative V sub gamma minus V sub dc, the diode turns off and acts as an open circuit. With zero loop current and no voltage drop across the resistor, V sub O remains constant at negative V sub dc. Plotting V sub O over a complete period shows that whenever V sub I exceeds negative V sub gamma minus V sub dc, V sub O holds fixed at negative V sub dc. When V sub I falls below the negative V sub gamma minus V sub dc, the output follows the negative peak of V sub I shifted upward by V sub gamma, before returning to the clipped level of negative V sub dc for the remainder of the period.